All right, now we're going to look at how we take significant digits and measurements and use those in mathematical manipulations and sort of some rules and some reasons why we use these rules when we're manipulating significant digits mathematically. So to start this, I want to get you an idea, feel for what we mean when we talk about precision. So let's imagine we have our object again. That's 5.2372 grams. And I'm going to measure it on my three different balances. And remember, my first balance is able to measure the plus or minus 1 gram. That's as good as it gets. This can measure all the way down to the nearest hundredth of a gram. And the third balance can measure all the way to the nearest 10,000th of a gram. Very precise balance. And if I take this object and I place it on this balance, it's going to record 5 grams. And that tells me the precision of the measurement is about 1 part in 5. That's not very good. If I take this object and I place it on this balance, we'll say it's going to measure 5.24 grams. Well, here I know the measurement to 1 part out of 524. I just ignore the decimal here. I just write the number on the denominator as the measurement without a decimal. And so plus or minus, I also write this number without a decimal. So plus or minus 1 out of 524. So I know this, this is 5, this is 500. So I have a precision here that's 100 times better than this one here. What's the precision in this measurement? Well, if I place that object on this balance, it's going to read 5.2372 grams. Take a little time to think about how would I convey the precision of this particular measurement? Well, I hope you see that that's going to be 1 out of 52,327. That's really precise. I know this to 1 part in about 50,000. That's 100 times more precise than this, which is 100 more times precise than this. So what I'm trying to convey here is there's a really good amount of precision in this particular measurement that's not here. And now what we're going to do is we're going to imagine that a student takes the object that we're measuring, we'll say it's these magnets or whatever, and it's going to take this object and it's going to find the density of it. So let's remember what density is. Density is the mass divided by the volume. So we're going to need to measure the mass of this object if we want to find its density. And we're also going to need to measure its volume. And let's say we were able to measure its volume very precisely. We were able to measure its volume, and its volume is going to be 1.934 milliliters. Just for the sake of the argument. All right, so we're gonna follow a student finding the density of this particular object using 3 different balances. Actually, 2 different balances, and let's just do it that way. Okay, so here, this student is going to say, okay, I'm going to use the balance that reads to plus or minus 1 gram. There's also a balance available that reads to plus or minus 0.01 grams. Okay, so the student takes the object, they place it on this particular balance here, and they say, well, that's 5 grams. All right, now they're going to calculate the density. So they calculate the density, and they calculate that as 5 grams divided by 1.934 milliliters. Let's see what that comes out to. 5 divided by 1.934. Well, I got a bunch of numbers in my calculator. How many should I write? This is what I get. 2.585315541 grams per milliliter. Should I write all of these? Well, no, of course I shouldn't. I don't know this number all the way out to here. That doesn't make any sense for me to report the density like this. But how should I report the density? Well, let's think about it. What is the worst measurement that I made? Was it this? You know, this has a pretty high precision of measurement. I actually know this number to about 1 in 2,000. Pretty close to that. But I only know my mass to 1 part in 5. So that tells me if I only know my mass to 1 part in 5, this is limiting how precise my density is that I should record. And because of that, I really should only report my answer to about 1 part in 5, which would be, well, I should probably round it up to 3. That'd be it. The appropriate measure for this density is going to be 3 grams per mil. And what we're seeing here is that when we do but when we do multiplication and division, what generally you see is your answer is going to reflect the lowest number of significant digits in the measurements that you made. So I only made this, this only has 1 significant digit, so my answer after I do a calculation should only have 1 significant digit as well. So to recap here, when you're doing measurements, what you report should represent the least precise measurement that you made. All right, now we're gonna do this again. This time, this particular student says, you know what? I'm going to take, let's say that we'll break it like that, okay. So they take the object and they place it on that balance. Just to make the math easy on me, we'll say it reads out at 3.24 grams. All right, and they say, oh wait, I forgot to measure the other parts. And they decide to put it on this balance. And this comes out to 2 grams. And then they add them together. Well, okay, we know how that works. 3.24 plus 2, that should be 5.24 grams, shouldn't it? Well, actually it shouldn't. And here's why. Because what I did when I took these objects and I measured it on this balance, I limited the precision of my measurement to 1 significant digit. I only know this good to the nearest ones place. And because I only know this measurement good to the ones place, why the heck am I recording the sum of these two to the nearest hundredths place? This is only good to the ones place. So I should really, when I add and subtract, truncate the addition at the level of least precision, which in this case is the ones place. This is not how this student should have done the measurement. What this student should have done is placed them all on the good balance, or I should say the more precise balance. And in this case, the measurement, we'll say would come out to 5.23 grams. Just happened to be this in this particular case. Now, if this student were to do this calculation, we would say, okay, we're going to take the density, which is the mass, which is 5.23 grams. We're going to divide that by the volume, 1.934 milliliters. And we should see that we're probably going to report the result to the nearest 3 significant digits, not 4. Let me do the math here. Let's see, 5.23 divided by 1.934. I'm going to write all the digits down, 2.70423992 gram per mil. We should not be doing this. We should be thinking about conveying the appropriate level of precision in our measurements, which looks like here, I know this number to about 1 part in 523, which is close to 270, yeah? So I should probably report this particular density as 2.70 grams per mil. This would be the appropriate number of digits to convey to people how precise were my measurements. Sort of to finish it off, you often tie the words precision and accuracy together, and those words mean different things. I've been using the word precision in talking about significant digits a lot. I haven't been talking much about accuracy, and they're different things. And so let's just take a little bit of time to discuss the difference between those two particular terms, accuracy, that is going to be how close your measurement is to the truth. How correct it is. Measurement. And instead of the truth, we're going to put the accepted value. Because we never really know if we're right or not in science. And precision, a way to think about precision is how repeatable your results are. So how agreeable to one another. How close your measurements are to each other. And so going back to our balance analogies, let's say I've got my object again, which is 5.2372 grams. I'm going to measure that on this balance, which measures to the plus or minus 1 gram. I'm going to measure it on this particular balance, which measures to the plus or minus 0.01 gram. And we'll say these balances are perfectly accurate to the level of precision that they're able to be. So let's see, if I place this one on here, it's going to measure 5 grams, but it could measure 6, depending on how the balance is calibrated. And so I see a range over which my measurements might not agree to one another, somewhere between 5 grams and 6 grams. So that's a precision of plus or minus 1 gram, which is pretty large. Over here, the measurements might be 5.22 grams all the way up to 5.24 grams. These measurements are going to agree to plus or minus 0.02 grams. So that gives a measurement, an indication of precision. Accuracy, however, let's say these balances are off a little bit. Okay? So let's say this balance, they all measure 10 grams too high, we'll say. Well, the precision is going to stay the same. It's still plus or minus 1 gram. So if it's off by 10 grams, this will measure anywhere from, say, well, that would actually be 14, right? 14 grams to 16 grams. That's way off. This is not an accurate balance. And this would measure anywhere from 15.22 grams all the way up to 15.24 grams. These measurements are close to one another, but boy, are they off. They're very far off. In an analogy with a dart thrower, here's a dartboard, here's a bullseye. This is a dart thrower that is precise but not accurate. They threw a dart here, missed the bullseye. Throw another one, and it's right there. Throw another one, and it's right here. Throw another one, and it's right here. These measurements, or these dart throws, are all very close to one another, very precise, but not very accurate. This is somebody who's neither precise nor accurate. This one's going to seem a little goofy. This dart thrower would be accurate, but not precise. Well, that seems odd, doesn't it? Now, how in the world would a dart thrower like this be accurate, but not precise? Well, it's not precise because the throws don't match each other very well at all. But imagine taking the average of these 4 throws. What's the average of these 2 throws? Right smack dab in the middle. What's the average of these 2 throws? Right smack dab in the middle. So if you take the average, the mathematical average of a bunch of different measurements, and they all, pretty much center on the agreed upon value, then we say that's accurate. It's not very precise because they're all over the map, but nevertheless, it's accurate. And of course, somebody who throws everything in the bullseye is both accurate and precise. And significant digits. When we're recording significant digits, those are a record of how precise your measurements are, not necessarily how accurate.